Yes, and welcome everybody to our last week of data structures. Today we're going to talk about, or we're going to finish up talking about the graph data structure and Dijkstra's algorithm. That last week we started talking about this, started talking about your risk assignment. This assignment again is due at the end of this week. And we went through most of the material that you need to complete the risk assignment. We talked about how to debug, especially focusing on bringing up those pictures of the board and being able to look at the pictures. We made it all the way through until the very last function that you have to implement, the shortest attack path. So how, if you're trying to attack an army on the other side of the world, how you go about doing that. And that's what we'll talk about today using Dijkstra's algorithm. As we do that, we will also see that there's another package called Heapdict that we'll be using for actually implementing Dijkstra's algorithm in this code. And so we'll take a look at how to use that package as well. So as a reminder, so yeah, this is the last week of class. Your assignment, your risk assignment's due this Sunday. And the very next day on Monday, I'll be posting your final exam. For the final exam, you'll have all of finals week to complete it. And basically the only requirement is going to be that you don't collaborate with anybody else, that you, but you will be able to use your computer, able to use any online resources, the textbook, or whatever other web pages are useful to you. But you will not be able to ask me questions, for example. And so if you do have any questions about anything in the class, then you'll want to make sure that you get those answered before the end of this week. And so Wednesday, we will have essentially all day as a review day for the final, plus I'll give a sort of a brief overview of the things that I think you should emphasize on your studying. And then Thursday for lab, you'll be able to either work on the risk assignment or ask questions about the final. But that's going to be pretty much your last chances to get these questions answered before the actual final. So my recommendation is that, again, I've given you out the practice final. If you haven't had a chance to take a look at that, definitely at least skim it until before Wednesday, so you have an idea of what things you might want to ask questions about. And we'll be going over that on Wednesday. So are there any questions about anything sort of administrative like that, about what to expect from the end of the course? And
Mike, how many points is the final worth?
Good question. So the final is going to be worth 40 points. You currently have about a little over 200 points in Sakai that everything adds up to. So the final will be worth roughly 20% of your grade. Good question. Any other questions so far? Okay, so then let me share my screen. And here we go. So again, I'm on the week 14 folder in our class GitHub repo, and we've talked about almost all of this stuff now. And what we're going to focus on now is Dijkstra's algorithm. Last time we left off talking about the breadth first search algorithm right here. And Dijkstra's algorithm and breadth first search are very, very similar algorithms. The basic difference is that this queue right here is going to be replaced by a priority queue or a heap. And so rather than doing a first in, first out, that we get things in the order that they came in, we're going to get things in the order of some sort of priority. And the priority is going to be based on the weights in the graph. And so in the case of risk, it'll be based on the number of armies in a particular territory. If we scroll down here, then this is the actual pseudocode that you'll be implementing and we'll be going over in detail today. And I've highlighted, so you notice these pluses. These just highlight the particular lines that have changed in the file compared to the previous pseudocode. And I've also put in uppercase the particular words that are actually different. So at the beginning, we're creating a priority queue, again, instead of a regular queue. A priority queue and a heap are, again, not technically synonyms. That the priority queue is the abstract data type. It's the thing that defines the interface. So it defines that you can get the smallest priority thing out. But it doesn't actually talk about the runtime. And the heap is the actual concrete implementation of the priority queue. So when you see priority queue, you can just think heap. And then we're looping over the priority queue now instead of the queue. And we dequeue, get out the smallest element each time. This will be the next territory that we're going to inspect and do this same procedure. So rather than continuing to go through here without a picture, we'll switch now over to an example graph and walk through the example graph. This example graph that we're going to look at comes from this file up here, graphs.pdf. This file contains some more example questions about what you might find on the final exam related to graph problems. So there are 4 problems in this file. I'm going to switch my screen right here over to this section right here. 4 problems here, all with 4 different graphs. Today we're going to go over just one of these, and you'll have the other 3 as practice that you can do on your own. The basic idea of this type of problem is that I'm going to give you the graph and expect you to sort of work through Dijkstra's algorithm, pen and paper, to give me what is the shortest path between any 2 nodes, or 2 particular nodes. And in this case, it's the S and the T node that we are trying to find the shortest path between. In this graph, you can see, first of all, that it's a directed graph. So it has arrows instead of not having arrows. This one down here, you can see, is undirected, no arrows in the graph. And then here, the weights are attached to each individual edge. Down here on problem 3 and 4, the weights are going to be attached to the nodes instead of the edges. So they're just, the algorithm's essentially the same in all 4 of these cases. It's just slightly different mechanics that you'll have to go through and slightly different things to think about. So make sure that you at least understand how to complete this sort of problem in all these cases. For this problem, working through it by hand, this is going to be really helpful for you as you're implementing this procedure inside of your final homework, because it'll, I think, really help crystallize for you what the pseudocode is doing and why it's doing that. So when you're doing the debugging, you know what exactly to look for to make sure that it's going correctly or not going correctly. But this is also the reason why on the final exam, I'm having you, you'll have a problem that looks like this, and you'll have to work through the algorithm manually. The reason I'm doing this on the final exam is because this is one of the really popular sort of questions to have on a coding interview. These coding interviews often divided into parts where you're actually writing code on a whiteboard or on a computer, showing somebody that you can actually create good code from scratch. But the other typical thing that you do is run somebody else's code, work through it, evaluate it, and Dijkstra's algorithm is one of the key algorithms that we do that for. That's because it has so many applications. We saw in those applications maybe 2 classes ago now. Google Maps is the key thing to keep in mind for this, but really, so we saw the airline routes and the 6 degrees of Kevin Bacon and internet routing, lots and lots of applications. Basically, every company that is hiring programmers somewhere has a Dijkstra's application inside of them, and so that's why it's one of the popular coding interview questions. Okay, so in order to work through this problem, what I'm going to do is switch my screen so that the graph here and the pseudocode are side by side, so we can refer to them at the same time. And then we'll get started. So in this pseudocode over here, so first we'll have a dictionary whose keys are territories, values are paths. So in this graph over here, it's not on the risk board anymore, so there's no territories and paths, but the edges correspond to two territories being connected, and the nodes themselves are the territories. So S is like our starting territory, and T is like our ending territory. Create a priority queue, and in queue our original S node into the priority queue, and it'll have priority 0. Inside of the priority queue, what this priority represents, so what this priority 0 represents, the value associated with each node in the priority queue, that represents the distance, the optimal distance, the shortest distance from the start node to that node in the queue. So the reason why the very first node, this S, is being added to the priority queue with priority 0 is because there is 0 distance between S and itself. So that's why it starts with 0. And then we'll have a set of visited territories, and we'll add the source to that set because we visited it. Okay, so in this while loop, we'll first dequeue the, let's see, right here, dequeue the current territory from the priority queue. So at this point, our priority queue only contains the set right here. It's our priority queue, and we dequeue that. And check, is it our target? Is it T? It's not T, so we're good. Come down here to this for loop. And for each of the neighbors, so A, D, and H, each of these neighbors, what we need to do is calculate the priority of the path from S to here. So in this case, since we're at the very beginning, the priority is going to be the distance from S to these nodes. And so in this case, it's 1 distance going to A, a 3 distance going to D, and a 2 distance going to H. For all of these nodes, what these numbers that I'm writing down represent, these are the values of the priority in the priority queue. So I'm not going to draw out that data structure separately somewhere else. I'm just going to write the actual priorities on top of the nodes themselves. And we'll see that as we go through the algorithm, this we'll be updating these values and changing them as we go through. On your final exam, I'm not going to be grading at all like the work that you do in order to compute the paths. It's just going to be essentially, did you get the correct path or not get the correct path? So if there's some other different notation that makes a little bit more sense to you, then feel free to use that. So each one of these nodes A, D, and H is now added to our priority queue, and the values associated with those nodes are 1, 3, and 2. When we come next to our while loop again, the priority queue is not empty because we have A, D, and H inside of the priority queue. And so we'll dequeue the next territory from priority queue. So dequeue the next node. And when we dequeue it, we always get the one with the smallest priority. So we get this 1 here, this A is the one that comes first. And I'm going to next perform this operation right here. So for each territory and its neighbors, the neighbors are B, E, and D. So the distance now from A to B is just 1, but the priority of B is not going to be 1, it's going to be 1 plus 1, so 2. The reason for that is the distance, the best distance that we've found so far from S to B goes through A right here, and so it's this 1 and this 1. One of the common mistakes that students make when working through Dijkstra's algorithm by hand is that you only put the most recent edge weight or the most recent priority right here as the priority of this particular node. But you have to make sure that it is the entire distance from your source, your start node, to whatever node you're going to. So we get a 2 right here. Similarly, looking at the E down here, we get a, there we go, 1 plus 5 is 6 right here. Looking at F, 1 plus 7 is 8. And then we come down to D right here. We do 1 plus 1 is 2. This is where it starts getting a little bit, you have to think a little bit. that the 3 right here, we could go from S to D, and that would give us a distance of 3 from S to D, but we have a shorter path going from S to A to D. S to A to D is 1 plus 1 for 2, and so we're going to delete D from our priority queue with value 3 and change it to have priority 2 now, because we can go from S to A to D. Let's see, I think now is a good time to stop and see if there's any questions about any of the steps that I've done so far.
Wait, why is the node with the lowest priority always first in the priority queue?
Let's see, this is a good question. So the question is, in our priority queue here at the very beginning of the second round, we had A, D, and H inside the priority queue, and 1 had the lowest priority. And so why are we going to look at the 1 first? The answer is that we'll end up getting wrong distances if we look at more expensive things first. So for example, if we looked at the biggest one first, we might go from S to H to L to M to T. And this path H to L right here has 17 in it. That's a big number. We'll see that our final distance from S to T is actually less than 17. And so if we ever even consider this path, then it means we've done something wrong. Since we're looking for the shortest path, you just always want to start with the smallest thing. This is sometimes called an example of a greedy algorithm. A greedy algorithm is one where you always do the thing that is at the current time what seems like it might be the best option, what's going to have the smallest penalty associated with it, or what is the most optimal thing to do just from that consideration. So that's sort of the intuition about why we would want to look at the thing with the smallest priority first. In terms of the pseudocode, like how does that happen in the pseudocode? It's when you say DQ the current territory from the priority queue. This DQ here, when you're using a regular queue, means just take out first in, first out. Whatever was the thing that was inserted, the longest time will go away. But when you're using a priority queue or a heap, when you say DQ, that means get the top element of the heap, get the thing with the smallest priority. So this line right here is what's causing us to select the A right here because it has the smallest priority. Good question.
Mike, how do we know, like, since like in the heap we only store the values, so it'll be like 1, 3, and 2 and stuff like that. How do we connect that back to the node A?
Yeah, this is a great question. So the question is, in the heap implementation that you made before, you were only storing particular values and not like items associated with those values. And for this assignment, we're actually going to use a different implementation of the heap than the one that you did in your previous assignment. This implementation will go over the code about how to use it here after walking through this example. But this implementation is going to store these, you'll be able to store values associated or store items associated with the values. So you'll be able to store the node associated with a number. Yeah, I've mentioned a few times that I've tried to simplify some of the things in this course for the online format to really just get you the things that you really need to take away from this class. And this is one of the things that we simplified a little bit, is the heap implementation made it just a little bit easier to do. It was a great question. Any other questions so far? Okay, so a quick recap of what we've done so far. The very first iteration, we looked at the node S, and then we considered all the neighbors of S. The second iteration, we looked at the node A. Again, we looked at A because it was the smallest priority, and then we considered all of the neighbors of A. Notice that we did not consider S again, and that's because S is not actually a neighbor of A, because the arrow is only pointing one way. So that's why we didn't even talk about S while we were talking about A. And then we updated, or we added B, F, and E to our priority queue with these associated values right here. And then we also updated the priority of the node D right here. It used to be 3, but we changed it to 2. And now we're ready for our next iteration of the loop. At this point inside of our priority queue, we have the B, the F, the E, the D, and the H. And actually, I should also say that because we have processed this A has been added to our to the visited set, the nodes that we have actually visited so far. And so I'll draw those with boxes around them so that we know what we've visited so far. So now we come to this line again where it says DQ from the priority queue. And again, this line DQ is always going to get us something that has the smallest priority. The very first iteration, there was exactly one node that had the smallest priority. But now there are 3 nodes that share the smallest priority. B, D, and H all have priority 2. And it's totally arbitrary which one you do next. It does not affect the correctness of the algorithm or the runtime of the algorithm. And so in the actual implementation of the priority queue, we would say this is an example of what's called non-deterministic behavior. Sometimes you might get the B next, sometimes you might get the D next, sometimes you might get the H next. There's no guarantee about what's going to come next. When you're working just pencil and paper, you can just pick whichever one either seems simplest to you or you want to do next for whatever reason. Doesn't matter. We'll just go in clockwise order. So we'll start with the B up here. And B only has one neighbor, this C right here. In order to calculate the distance to C, it's 3 plus 2 gives us 5. I used the 2 right here, the priority of B, and not the 1 over here. This is another sort of common mistake that's really easy to make when working through this by hand, is you have to make sure that, again, the number that you associate with each node, the priority of each node, you always make sure that that is the distance from that node to the start. So 3 plus 1 plus 1. And that's a way that you can always check your work, is by going actually walking backwards 3 plus 1 plus 1 and counting to make sure that it's whatever number you put right here. In practice, in your actual code though, you don't want to have to retrace your steps all the way back to the start every time. And so you just add to the previous priority right here. 3 plus 2 gives us 5. And we can do that because this 2 is equal to this 1 plus this 1. And that's the only neighbor of B right here. So we can go ahead and add that now to our visited set, and we're done. Now we have C, F, E, D, and H in our priority queue. Again, sometimes the nodes in the priority queue are called the frontier of our algorithm. These are the nodes that we're considering at every iteration of this while loop. You'll see the book or online resources use that word frontier occasionally. Now, there's only 2 nodes that have this shared minimum value of 2, and so we pick between D and H, whichever one we want to do next. We'll continue in this clockwise order though and do D next. For D, it only has one neighbor, this E right here. Again, H is not a neighbor of D because of the direction of the arrow, so we're not going to consider H. We're only going to consider E. And we have to think about what is the distance to E. Well, it's 3 plus 2. The distance of the edge plus the previous priority of the node that we're looking at. So 3 plus 2 is 5, and 5 is less than 6. So we take out that old 6 priority and put a 5 right here. And now D is the node that we would travel to get to E. Let's go ahead and add D now to our visited set like this, and on to our next iteration. Now we have H, E, F, and C, these 4 nodes in our priority queue. The smallest one is H right here with priority 2, and so let's consider that. H has 2 neighbors, L and I. I will have distance 1 plus 2 is 3. L will have distance 17 plus 2 is 19. And we also, D is now a neighbor of H, but one of our conditions in this for loop right here is that we only consider the neighbors, I'll have to scroll over to see this, only consider the neighbors that are not in the visited set. So because this D is already in the visited set, it means that we've already found a path that is at least as short as whatever path we might find here. So we don't have to even consider it at all. And we only have to consider these 2 here. If you think about it a little bit, you can sort of justify to yourself that because we've always been picking the smallest thing from the priority queue, there's no way that this path right here could ever be smaller than whatever number we had right here. Otherwise, we would have already done that path because we've been picking the smallest path every time. That's a property of Dijkstra's algorithm that if this were a graduate level algorithms course, we would prove that about the algorithm. But here, our goal again is just to get the intuition, not to prove it. So that is the H added to the priority queue. And now we have L, I, E, F, and C all in the priority queue. We look at the smallest one. 3 is the smallest one. This I right here. This I has no neighbors, so there's nothing to do. Just add that to our visited set, and we're done. We will pause at this point to see if there's any questions about anything at this point. Okay. So the remainder of the procedure of solving this is going to be essentially the same of what we've done before. We'll just keep walking through it, and we'll be done in a minute or 2 here. The smallest in our priority now is C and E, both at priority 5. And so it doesn't matter which one we pick. I'll pick this E1 first. And here, when we go from E, E has only one neighbor, J, but there's 2 different paths that we could take to J. And this is really just been added here as a potential source of confusion for you. When you have 2 different paths from one node to another, you want to make sure that you're always just taking the smallest of these 2 paths. You don't add these 2 values together. It's not 5 plus 7 is 12. It's you can take one of them. You can take this one, the top one, or the bottom one. And so if we're looking for the shortest path, you would always take the top one here. So the distance from E to J is 5, and we calculate the distance from S to J by this priority 5 plus this 5 right here and get a 10 down here. And add E to our visited set. Next, looking at our C, F, J, and L nodes. C is our lowest priority, so let's consider that one next. We have B over here as a neighbor, but it's in the visited set, so we don't consider it. We have F down here as a neighbor. 2 plus 5 is 7. That's less than 8, so we can delete this 8 and replace it with a 7. Down here, K, we would have 5 plus 7 is 12 to get to K. And then C down all the way down here to O, 5 plus 2 is 7. And that's all of them. So let's add that to our visited set. Again, not considering G because the arrow points the wrong way. In our priority queue now, we have O at 7, F at 7, J at 10, and L at 19. So F and O both equal in priority. Let's just do F first. F has only one neighbor right here, J. And so we have 2 plus 7 is 9. That's less than 10, so cross that out and put the 9 right here. Add F to our visited set. Now, our O down here is the node with the smallest priority. And so let's consider that one next. Go ahead and switch colors to something that's a little bit more readable. Here, O has T as its neighbor, and so 7 plus 9 is 16 for T. And here is another one of the common mistakes that students run into, is that as soon as you hit T, you just stop, you say that you found the shortest path and you're done. But we'll see actually that there is a path shorter than 16 that you can use to get to T, and so you don't want to stop as soon as you hit T. This is a very common error both when working through it in pencil and paper like this and when coding. So you have to make sure that your if statement really is in the right place for doing this stop check. The correct spot for it is right here. And so it's as soon as the current territory is the target. So current territory is the node that you've popped off the priority queue. Here, when we're visiting the neighbor of O and checking that it's T, that's down here that we're visiting all of these neighbors in this for loop for all the neighbors. T is one of the neighbors. T is not this current node yet. T is not the thing that came off the priority queue. And so that's why we're not done yet. Other neighbor of O up here is K. 7 plus 2 is 9. So let's cross out that 12 and add a 9. And that's all of the neighbors of O. We'll add it to the visited set now. So we have K, J, and L here in our priority queue, a 9 and a 9. Consider both of those. And so we'll do let's do K first. K to T is 2 plus 9 is 11. 11 less than 16, cross that out and put 11 right here. And up here, F is a neighbor, but it's in the visited set, so we don't visit it. G is not a neighbor, C is not a neighbor, so we don't go in those directions either. There we go. And now J is our, we have J and L in our priority queue. We'll consider J next because it has the smaller priority. And the neighbors of J are T and M. For T, 9 plus 2 is 11, so it's actually the same priority, and so we don't need to modify the priority at all. If we go down here to M, then it would be 9 plus 2 again, 11 for M. Now the only 3 nodes in our priority queue are the T, the M, and the L, and the T has the smallest priority of 11, and so this could potentially be popped off from our priority queue at this point because it's one of the smallest. We might pop off the M or we might pop off the T. And I guess I'm saying pop off instead of DQ. They're essentially synonyms, both meaning taking whatever this is the next element. DQ is probably a little bit more technically correct to say, so I should be saying DQ. And okay, so we will DQ the T next, DQ the T, and now in this if statement right here, because we have just DQ'd the T, we're checking to see if it is the target, and it is, so we're done. And so the length of the shortest path from S to T here is 11. At this point, we haven't talked about exactly what the shortest path is. We've only talked about that the length is 11. And we'll talk about exactly what the path is next and how to compute it. But are there any questions at this point about where this 11 came from? Okay. So then the last thing for us to talk about is actually the, not just the length of the path, but the actual path itself. And there are 2 ways to think about this, depending on what makes the most sense to you. So I'll go ahead and walk through both of them. The first one is that you can walk backwards from T, always taking the best possible route at any given moment. So walking backwards from T, we see that there's these two routes that we came from, this 2 and this 2. I'll go ahead and draw them in green up here like this and like this. And then this K route like this came up here and backtracking all like that. That was one of the routes that we took. And then here T to J, and then J, the shortest path coming from that was to F. From F, let's see, we did the C path like that, and yeah, and then we connected to C and back like that. So we had two shortest paths, one being T, and I'll go ahead and write it backwards, T, O, oops. T, K, O, C, B, A, S is one path, and the other path was T, J, F, C, B, A, S. And both of these had the same length of 11. When I ask you this problem on the exam, it's possible there will be one path, it's possible there will be multiple paths like this. If there are multiple paths, I want you to actually provide all of those paths. This is sort of an ad hoc way to calculate these paths. It's not what's in the pseudocode here. But if doing it in an ad hoc way like that makes sense to you, that's a fine thing to do. A little bit more closely related to what's in the pseudocode right here is that we have this dictionary up here, and we hadn't talked about this dictionary at all yet. What this dictionary is doing is this is keeping track of the actual path from any from the source node to whatever nodes we're looking at that is going to be the shortest path to that particular node. That the value of this dictionary, sorry, the key of this dictionary first is going to be the territories or the nodes, and then the value is going to be a path from the source to that node. That is the shortest path, or a shortest path. And in order to maintain this dictionary, keep it accurate, we have to be adding to it as we go through our sort of initial pass through the diagram, calculating the actual priorities associated with each node. And what we do is we just keep track of, let's see, I'll go ahead and scroll down to the next problem to illustrate it. When we're at node S up here on our first iteration, our visited set, now I visit A and D and H, and not only do we write the numbers above them, 1 and 3 and 2, but we also actually draw the path to those nodes like this. And then we'll pick A as our next node and consider its neighbors. We have B of 2, draw the path, F of 8, 1 plus 7 is 8, draw that path. E would be 6, 1 plus 5 is 6, draw that path here. And then here's where it gets tricky, maintaining this dictionary of paths. When we go from A to D, it's 1 plus 1, so it's 2. So we will add this path down here, but now we'd have to actually delete this path right here. And it's a little bit hard for me to do with my pen stylus. So this would be easier to say pencil and paper. You could actually erase it. But now this path goes away because I set the path, set dictionary of D equal to the path DAS. This lines right here, this if statement is what's actually maintaining that dictionary for us. And this will be a key thing to make sure that you get correct in your code when you're implementing this, that you want your dictionary of the path. So the thing that you set dictionary at D to be equal to is first the previous path up here, and then adding a single territory. You're not going to just have it be just the last territory or just the last edge. You're going to have it be the entire path, everything that you've considered so far. So copy is everything that you've considered so far, plus the most recent territory. Are there any questions about actually getting the paths, either what this dictionary is doing in the pseudocode or the more ad hoc method that I did up here? Okay. So again, there's 4 of these problems. The difference is just, so like the edge structure in all of these is the same. It's just whether it's directed or undirected and whether the weights are on the nodes or the edges. So I just want to make sure that you're able to do any of these cases, because I could ask any of these on the final exam. But let's see. This one down here, problem 4, is the one that most closely resembles what the actual risk problem is, that the weights are on the territories themselves, and all edges are bidirectional, not directed. My hope is that this will be one of the easier problems on the final exam, that it should be relatively straightforward, that you can just walk through the procedure, write out the answer, and you get full credit. It's not going to be like the say problems related to big O notation or things where there's going to be a lot of very subtle calculations going on. So the last thing for us to talk about today and for this homework assignment is how to use a priority queue in Python. And I mentioned a little bit ago that you're not going to be using the priority queue that you implemented in the previous assignment. Instead, we'll be using one that's a little bit more standard and featureful. It's not built into Python, but it is a common package that lots of people use. Let's see, before going on to actual Python code, are there any other questions about the pseudocode or the pictures? Okay, so on to Python and code. I have a terminal open here, and I'm in our risk repository right now. And the first thing that I want us to look at is this requirements.txt file. So again, this file contains all of the packages that are needed for any to work with the project. Matplotlib is the library that's doing the graphing, drawing all of these game boards for us. PyTest is the same testing framework that we've been using for all of this whole class. And heapdict is this library that we're going to examine right now. And I'll just load up Python 3 like this and import heapdict like that. In this heapdict is whenever in the pseudocode you see priority queue, it is referring to this heapdict type right here. In code, whether it's Python code or any other language, it's sort of customary to name our priority queues just with the letter Q, because it's short for QUE as the queue, and that is short for priority queue. So I'll say Q equals heapdict dot heapdict like this. This constructs the actual queue for me, and it has nothing inside of it. You can see what's contained inside of a queue by doing something like that, converting it into a list or converting it into a dictionary. And you can see that it just doesn't have anything in it yet. In order to add a new element into the queue, there is no insert function that you want to use. Instead, you add a new element just like you add a new element to a dictionary. So let's say I have a node A, and I want to set its priority to 3, I do that. And if I have a node B and I want to set its priority to 2, I do that. And then a node C, set its priority to 5, I do that. Now, in order to see what's in the queue again, if you just do queue like that, you get this ugly thing because this is what's in the dunder repr function of the heap class. And so in order to see its contents, we would convert it into a list or a dictionary. If we convert it into a list, we just get the keys like this. We don't get the actual values. We don't get the priorities. And so in order to see the priorities, you can convert it into a dictionary like that. And so at this point, it's basically behaving exactly like a Python dictionary behaves. The difference between a heap dict and a Python dictionary is that the heap dict has this, this method built in called peak item. So q.peak item like this. And q.peak item is guaranteed to always give you back the item that has the smallest priority. So here, this B has priority 2. It's the one that I inserted up here with the smallest priority. And so when I do q.peak item, this is what I get back. Notice that it's not related at all to the order that I inserted things in. Peak item also does not remove anything from the priority queue. If I do dict of queue again, you see that it still has the same results in it. Let's say I add a new item inside of it that has a smaller priority like this, then q.peak item will now give me that smaller priority, and it still has not removed the B. That B stays in there. In order to actually remove something from the heap dict, what you do is do q.pop like this. But this is kind of a little bit of a weird functionality, not the way that I would have designed this library, but pop by itself doesn't actually do anything. You have to pass in the particular value that you want to pop off. So in particular, you have to pass in the minimum value. So after we've just called q.peak item right here to figure out what the minimum was, now to actually remove the minimum from the dictionary, you'll do q.pop and then pass in D like that. Tells us what the actual value was right here, but now it's actually removed that that D value from my dictionary. And now if I do q.peak item again like this, we're back to B being the minimum. Q.pop B like this, and now q.peak item, we're getting A as the minimum. You can also get the number of elements in your priority queue like this, and that's totally fine. One last syntax thing that you'll need for the assignment is you'll need to be able to update the priorities in your priority queue. And so let's say we have, again, this is our current values of our dictionary, but we're going to revisit this C node. And when we revisit it, it turns out that its priority changes. So if we do Q C like this is now equal to 1, then it updated that C value for us, just like you would expect from a dictionary. And this q.peak item now, it used to give us A, because A used to have the smallest priority, but now it gives us C because C has the smallest priority. Dustin, go ahead.
I was wondering if you can index the output from peak item. Let's say you wanted to get the A out. You don't have to like manually type it in each time. You want to pop it off.
Sorry, can you rephrase that? I'm not sure what you're.
So when you call like peak item and it gives you like C as a string in 1,
Yep.
how do you just like pull the C off so you can like put it into?
Oh, great question. So basically just get this C and ignore this one.
Yeah.
So this here is a tuple, a Python tuple, just like any other Python tuple, and we can manipulate it however we want. So one option is that we could do something like q.peak item at position 0, getting us the C. If we did at position 1, it would give us the actual priority. Another option is that we could say node, comma, priority equals like this, and now node contains C and priority contains the number. So these are just, yeah, it's just a tuple. You can, either of these two things will work. I think in my solution, I find this to be a little bit nicer than calling the peak item function every time. It turns out in the implementation of peak item, it's a really fast implementation. So there's not really much overhead of doing it like this. But if peak item were a little bit like not so fast of an implementation, then doing something like this would be a little bit faster because you avoid doing it twice. Good question. Let's see.
Mike,
Yes.
can we pop any value, or is it just the smallest?
Question is, can you pop any value off, or is it just the smallest? And you can pop any value off. That's why it's explicitly requiring you to pass in the particular, the key right here. You can pop any key off. For your assignment, the only ones that you'll need to actually remove will be the smallest. You never want to remove anything from the middle.
Right, so like if it's popping a value that's not the smallest, wouldn't that be really slow?
Yeah, so the implementation of this is different than the type of heap that we implemented in our assignment. But yeah, you're right that if you can pop off any value for the standard binary heap that we implemented, then that would be a linear time operation and be very slow. I think I very briefly mentioned that there are lots and lots of extensions to heaps. So just like the AVL tree is an extension to the binary search tree, there are many other extensions to the heap that are typically used in practice rather than the vanilla heap. And those other extensions allow things like efficiently removing from the middle without paying a linear time penalty. Yeah, so it's a great question, great connection to our previous material that we've talked about, but they're implementing something slightly more complicated. So yeah, all great questions so far. Any other questions about this heap dict container and how to use it or what it can do? Okay. Maybe I'll just come back to our code really quick and just highlight again that here the deck in this line here, that's where you'll do the peak item and the pop. And then down here, the syntax is going to look basically exactly like I have it written out here, that it'll, it's just, oh, let's see, this is the dictionary. Here's the, update the territories priority in the priority queue right here with the new priority. This line is going to use that dictionary syntax of something that looks like this, but instead of the territories, it will be the priorities being added together.
When you say in the first line, create a dictionary whose keys are territories and values are paths, is that an empty dictionary to start?
Yeah, great question.
Or...
So this will just be an empty dictionary. It's just any time that you have a dictionary, you need to know like what's the semantics of that dictionary. And so you need to say like, what does it mean for something to be a key and what does it mean for something to be a value? And so that's why I just wrote this out. But you're right, this will be an empty dictionary right here. And here you'll add the very first item to the dictionary.
Okay, thanks.
Any other questions about anything at all? Okay, well then that is all the material that we are covering in data structures. I think we'll just stop class here for today, and on Wednesday we'll start our review session going over, I'll have a few things that I think that I want to highlight for you, things to emphasize what you should study for the final exam, but I'm mostly going to expect that that time on Wednesday and on Thursday in the lab is for you all to ask questions. And so if you don't have any questions to ask, then great, we'll have a short class period. But hopefully you'll have lots of good questions. I'll stick around now to ask questions either about final exam stuff or the risk homework assignment, and I have office hours right now as well. But otherwise, I will see you all on Wednesday.
Thanks, Mike.
Thanks, Mike.
You're welcome.